You know, when we're working in this section of the book and we have this nifty little title here that says anti-differentiating with partial fractions, it's easy just to jump right in and start doing that. But keep in mind that if you were on a comprehensive exam and you saw this problem, the first thing you should try is recognition. Obviously, you can't recognize the antiderivative of that. But the second thing you want to try is a substitution, either a trig substitution or a u substitution. So don't automatically jump to partial fractions when you have a quotient like this. Go through those first two things because they're so much easier to do. Let's just try that real quick. And naturally, we would pick the denominator to be our u, so we would get u squared minus 1. And then the derivative of u with respect to x is going to be 2x dx. And you see that we need a 2 and an x. The 2 we could fix, but we have a lot of stuff right there that we couldn't use to replace with du. So it doesn't take much effort to realize that the u substitution is not going to work here, but it's something that you do want to take a look at. So that failed, and so our only hope now is for partial fractions. Integration by parts would be the other thing, but integration by parts usually is a product, and integration with partial fractions usually goes with having a quotient, or it always has to deal with a quotient. So the technique for partial fractions says that the degree of the numerator needs to be less than the degree of the denominator. Obviously, it's not in this case, but there's something that we can do. We can divide this fraction to simplify it. We can't use synthetic division because synthetic division requires you to have a linear divisor, and we do not. We have a quadratic divisor. So we're just going to have to use long division here. I know that that strikes fear in your heart, but it's going to be okay. This is going to be an easy one. We do need some placeholders here. I'm not going to specify what they are, but since we're missing a whole bunch of exponents there, just leave some space for your like terms when you do the division. Just as a review, we're going to take this first term and we want to make it look exactly like this. So I ask myself, what do I need to multiply by x squared to get 3x to the fourth? And I'm going to need 3x squared. Now I need to multiply this times each of these terms and write them down below. So 3x squared times x squared is 3x to the fourth. And 3x squared times negative 1 is negative 3x squared. That's where my placeholders come into play. I don't have any x squares up there, so I'm just going to be adding that to 0. Now when you're dividing and you multiply on the outside, then you have to subtract this number right here. Notice these are the same things. If we start adding, we're going to get more of that. We don't want more, we want less. So we have to remember to subtract, not just the first term, but subtract that entire line, which changes all of the signs. The first terms always go out, and then you add and bring down anything that's left over. So now we have 3x squared plus 1. Do the same thing again. What do I multiply by x squared to get 3x squared? So I need a plus 3. And a positive 3 times x squared is 3x squared. And a positive 3 times a negative 1 is a minus 3. Now again, we want to subtract that line from the line above it, so change all your signs. And these terms will go out, and a 1 and a 3 leaves a 4. You can't divide x squared into 4, and so this is just your remainder. So think about how you write a remainder. This integrand is equal to this quotient plus the remainder divided by the divisor right here. So I can rewrite my integral now as 3x squared plus 3 plus 4 divided by x squared minus 1 dx. So this integrand looks a lot different, but it's equivalent to this right here because we've just simplified that division. Now remember that you can integrate term by term. So the 3x squared we can integrate just using recognition. If we add 1 to that power and divide by the new power, then we're going to get x cubed. And then the 3, same thing. That's going to be plus 3x. But when we integrate the 4 over x squared minus 1, then we're going to have to use some tools on that. Recognition is not going to work. If you try a u substitution, then your u would be x squared minus 1, and your du would be a 2x dx. And you can see we don't have an x in that numerator to use up. So that means that we want to use our partial fractions on this term right here. So don't lose your x cubed plus 3x. I want to factor that denominator, and each of the linear factors of the denominator is going to be a denominator of your sum of fractions. So I'm going to have x plus 1 and x minus 1 because that's the difference of squares. I need some numerator for this fraction, and I need some numerator for that fraction right there. Okay, so I'm going to multiply a times the denominator of the other fraction, x minus 1. I'm going to add to that b times the denominator under a, x plus 1. And that has to equal the original numerator, and the original numerator is 4. Next, I want to zero out this first term, so I'm going to let x be 1. And then I'm going to go ahead and write my next step, which is to let x be negative 1. If x is 1 right here, then that zeroes that term out, and 2b, because x is 1, which makes that 2 times b is equal to 4, which means that b is equal to 2. If I let x be negative 1, then I'm going to get negative 2 times a. This term is going to reduce out, and that's equal to 4. So a is equal to negative 2. So now rather than use up space, I'm going to go up here and erase those and replace them with the numbers. So a is negative 2 and b is 2. And now I can integrate these. Just like we integrated these term by term without rewriting them, you don't have to rewrite them with separate integrals. But here's what we're going to do. You can write this in. We're going to integrate this term, and we're going to integrate this term right here. Now the negative you can bring out to the front, or you can leave on the inside. It really doesn't matter. Now our partial fractions have given us things that we can integrate using our other tools. We still have these terms out front that have already been integrated. And then we can use a u substitution on this. When we have this really simple denominator where the du is equal to dx, then sometimes you don't have to write out those steps. We'll write it on the first one, and on the second we'll just kind of work through it. But we want to choose the denominator to be our u. That means that our du is going to be 1 dx. So you can see that the negative 2 is just a constant multiple that can be moved out to the front. And since dx is the same as du, I have du on the top. And then x plus 1 is the same thing as u. So what I'm integrating is negative 2 times the integral of 1 over u du. And the negative 2 is a constant multiple. The antiderivative of 1 over u du is natural log absolute value of u, and u is x plus 1. Because du is equal to dx there's really not a fix that goes with that. So when we go to this next one over here, we can kind of realize that the 2 is just going to be a constant multiple in the same way. And then I'm going to have 1 over u du because my du and dx are the same thing. So I don't have to write these steps out unless you want to. It doesn't take long to write them out. But this one is going to be natural log, absolute value, x minus 1. And then plus c because this is an indefinite integral.